Software architecture. In this video, we are going to see about software architecture. The software architecture activity corresponds to a macro design approach for creating models that depict the quality and function of the software system. It provides black box models used to evaluate the system's projected capabilities as well as its expected quality, all from multiple perspectives. Therefore, architectural designs allow different stakeholders with different backgrounds and expertise to evaluate the design and ensure that the software architecture is addressing their concerns. For example, from the systems engineering perspective, architectural designs can provide information about the physical deployment of the system, including subsystems located at different locations, the artifacts executing in the subsystems, and how the system as a whole communicates. From the configuration management perspective, architectural designs can provide information about the hierarchy of files in the file system and how these files are interconnected to build and deploy the software system. From the software engineering perspective, different architectural designs can help decompose the software and define the major structural components of the system, identify interfaces between the components, map the requirements to them, evaluate concurrency issues, and provide overall insight into the design solution. A major benefit of architectural designs is their capacity to evaluate high-level concerns from stakeholders that deal mostly with the non-functional requirements, for example, performance, usability, security. For these purposes, architectural designs serve as important communication, reasoning, and analysis tools that support the development and growth of the systems. Software architecture lays the foundation for all subsequent work in the software engineering lifecycle. Modular design. In this video, we are going to see about modular design. A modular design reduces the complexity, facilitates change, and results in easier implementation by encouraging parallel development of different parts of a system. The concept of functional independence is a direct outgrowth of modularity and the concepts of abstraction and information hiding. In simple word, a modular design implies that the problem has been decomposed into a set of modules that have only limited interactions with each other. Decomposition of problem into modules facilitate taking advantage of the divide and conquer principle. Functional independence is achieved by developing modules with single-minded function and aversion to excessive interaction with other modules. Independence is measured by cohesion and coupling. Cohesion is a measure of relative functional strength of the module. Coupling is a measure of the relative interdependence among modules. A design solution is said to be highly modular if the different modules in the solution have high cohesion and their inter-module couplings are low. A software design with a high cohesion and low coupling among modules is the effective problem decomposition. Coupling. In this video, we are going to see about coupling. Coupling between two modules is a measure of the degree of interdependence or interaction between the two modules. A module having high cohesion and low coupling is said to be functionally independent of other modules. If two modules interchange large amounts of data, then they are highly interdependent. The degree of coupling between two modules depends on their interface complexity. The interface complexity is basically determined by the number of types of parameters that are interchanged while invoking the functions of the module. Classification of coupling. Even if there are no techniques to precisely and quantitatively estimate the coupling between two modules, classification of the different types of coupling will help to quantitatively estimate the degree of coupling between two modules. No direct coupling, data coupling, stamp coupling, control coupling, external, common coupling, content coupling. Data coupling. Two modules are data coupled if they communicate through a parameter. An example is an elementary data item passed as a parameter between two modules, for example, an integer, a float, a character, etc. This data item should be problem related and not used for control purpose. Control coupling. A control coupling exists between two modules if data from one module is used to direct the order of instruction execution in another. Common coupling. Common coupling, also known as global coupling, occurs when two modules share the same global data, for example, a global variable. Content coupling. Content coupling, also known as pathological coupling, occurs when one module modifies or relies on the internal workings of another module, for example, accessing local data of another module. Therefore, changing the way the second module produces data, that is location, type, timing, will lead to changing the dependent module. Stamp coupling. Two modules are said to be stamped if they communicate using a composite data item such as a record, structure, object, etc. For example, passing a record in Pascal or structure variable in C or object in C++ language to a module. Process-oriented design. In this video, we are going to see about process-oriented design. The process concept is used when the system requirements demand that several tasks be carried out simultaneously. Concurrent programming is important in real-time computing, that is structural parallelism, and as well as parallel computing, that is fine-grained parallelism. The decomposition of the software system into processes is the most important design step, particularly for real-time systems. Real-time systems communicate with their environment, that is, a technical process which is controlled or another node in a distributed system, and processes represent components of the environment in a software system. Normally, process-oriented designs are completed by data or function or object-oriented design components. Processes use functions to transform data and perform operations on an object. The concept of a module is very closely related to program design. Modules are elements which are individually named and addressed. These elements are normally identical to components defined during the architectural design. A good design is characterized by a strong cohesion between the parts of a module and weak coupling between parts of different modules. In data or function-oriented designs, modules are composed of functions which are similar or manipulate the same set of global data space. In data-oriented design, a module consists of a data object and the functions which manipulate it. In object-oriented design, an object is identical to a module. One or more processes can comprise a module. Process and optimization. In this video, we are going to see about process and optimization. In varying degrees, process optimization goes on at all levels of maturity. With the step from the managed optimizing, however, is a paradigm shift. Up to this point, software development managers have largely focused on their products and will typically gather and analyze only data that directly relates to product improvement. In the optimizing process, the data is available to tune itself. With a little experience, management will see that process optimization can produce major quality and productivity benefits. For example, many types of errors can be identified and fixed far more economically by design or code inspections by testing. Unfortunately, there is only limited published data available on the costs of finding and fixing defects. However, from experience, I have developed a useful rule of thumb. It takes about 1 to 4 working hours to find and fix a bug through inspections and about 15 to 20 working hours to find and fix a bug in function or system test. To the extent that organizations find that these numbers apply to their situations, they should consider placing less reliance on testing as their primary way to find and fix bugs. However, some kinds of errors are either uneconomical to detect or almost impossible to find except by machine. Examples are errors involving spelling and syntax, interfaces, performance, human factors, and error recovery. It would be unwise to eliminate testing completely since it provides a useful check against human frailties. The data that is available with the optimizing process gives us a new perspective on testing. For most projects, a little analysis shows that there are 2 distinct activities involved: the removal of defects and the assessment of program quality. To reduce the cost of removing defects, inspection should be emphasized together with only other cost-effective techniques. The role of functional and system testing should then be changed to one of gathering quality data on programs. This involves studying each bug to see if it is an isolated problem or if it indicates design problems that require more comprehensive analysis. With the optimizing process, the organization has the means to identify the weakest elements of the process and to fix them. At this point in process improvement, data is available to justify the application of technology to various critical tasks, and numerical evidence is available on the effectiveness with which the process has been applied to any given product. We should then no longer need reams of paper to describe what is happening, since simple yield curves and statistical plots could provide clear and concise indicators. It would then be possible to assure the process and hence have confidence in the quality of the resulting products. Data-oriented design. In this video, we are going to see about data-oriented design. In data-oriented design, a system's data requirements drive the design. Entities are determined for each subsystem, then entity interrelationships are examined to develop the additional entities needed to support the relationships. The process iterates until the entity relationships can no longer be expanded. Data-oriented design is also known as information engineering. Analysis is performed on a system's data entities to extract data requirements. The data requirements then drive the program design. Data-oriented design is useful for systems that process lots of data and that will be programmed using a procedural language such as COBOL, for example, database and banking applications. Various elements of data design are data object, databases, data warehouses. Data object. The data objects are identified and relationship among various data objects can be represented using entity relationship diagrams or data dictionaries. Databases. Using the software design model, the data models are translated into data structures and databases at the application level. Data warehouses. At the business level, useful information is identified from various resources, from various databases, and the data warehouses are created. For extracting or navigating the useful business information stored in the huge data warehouse, then data mining techniques are applied. Guideline for data design. Apply systematic analysis on data. Represent data objects' relationships among them and data flow along with the contents. Identify data structures and related operations. For the design of efficient data structures, all the operations that will be performed on it should be considered. Establish data dictionary. The data dictionary explicitly represents various data objects, relationships among them, and the constraints on the elements of data structures. Defer the low-level design decisions until late in the design process. Major structural attributes are designed first to establish an architecture of data, and then low-level design attributes are established. Use information hiding in the design of data structure. The use of information hiding helps in improving the quality of software design. It also helps in separating the logical and physical views. Apply a library of useful data structures and operations. The data structures can be designed for reusability. A use of library of data structure templates called as abstract data types reduces the specification and design efforts for data. User interface design process. In this video, we are going to see about user interface design process. The user interface design, like all other software design elements, is an iterative process. Each step in this design occurs a number of times, each time elaborating and refining information developed in the previous step. Although many different user interface design models have been proposed, all have the following steps in common. Using the information stated in the requirements document, each task and actions is defined. A complete list of events, that is user actions, which causes the state of the user interface to change is defined. Each user action is assigned iteration. Each user interface state as it will appear, look to the user, is depicted. Indicating how the user interprets a state of the system using information provided through the interface. To sum up, the user interface design activity starts with the identification of user, task, and environmental requirements. After this, user states are created and analyzed to define a set of interface objects and actions. These objects then form the basis for the creation of screen layout, menus, icons, and much more. While designing the user interface, the following points must be kept in mind. Any interface that fails to achieve any of these rules to a reasonable degree needs to be redesigned. Determine how the environment, like operating system, development tools, display properties, and so on. Real-time system. In this video, we are going to see about real-time system. The behavior of real-time systems is based on timing constraints. Real-time systems are those systems which monitor and control their environment. These systems are usually associated with some hardware devices. There are two important elements of the real-time system. Sensors. They are responsible for collecting the data from the system. Actuators. These are responsible to change the environment of the system. Real-time system is a software system in which the correct functionalities of the system are dependent upon results produced by the system and the time at which these results are produced. Real-time systems must respond within specified time. Real-time software design. In real-time systems, there is one class of the system in which on giving the stimulus, the system produces the response. The stimuli can be of two types. Periodic stimuli. These are the stimuli that occur at periodic time interval. For example, pressure sensor may be activated after every 20 seconds. Aperiodic stimuli. These are the stimuli that occur at unpredictable time interval. For example, power failure in the system. Different stimuli require different time intervals. Hence, the real-time system architecture should be such that their fast switching between the stimuli handler should be allowed. Real-time systems are designed with the help of many cooperating processes. System design. In real-time system design, both the hardware and software systems are designed. Then, functionalities are identified and classified in hardware or software. The system design decisions can be made based on non-functional requirements. Hardware and software design. The real systems can be designed in the stages as timing constraints. The timing constraints are applied to various classes of stimulus response systems. It is checked that whether these timing constraints are being satisfied by the system. The timing constraints suggest that certain design strategies cannot be applied to avoid additional overhead involved. The low-level programming features can be used in system design for improving the performance. State machine modeling. On triggering some stimulus, the system may transit from one state to another state. Hence, to model the real-time systems, the finite state machines are used. But drawback of this design is that it gives a complex model even for the simple systems. Some UML notations can be used in FSM for modeling the real-time systems. Real-time programming. For programming hard real-time systems, the assembly language is used. The assembly languages are used when strict deadlines has to be met. The C language is also efficient for real-time programming, but C does not support concurrency and shared resource management. Architectural designing. In this video, we are going to see about architectural designing. Architectural designing is a process of decomposing a large complex system into a small subsystems. These subsystems are meant for providing some related services. The architectural design is basically a layout or a framework of the system for subsystem control and communication. The requirements of the software should be transformed into an architecture that describes the software's top-level structure and identifies its components. This is accomplished through architectural design, also called system design, which acts as a preliminary blueprint from which a software can be developed. IEEE defines architectural design as a process of defining a collection of hardware and software components and their interfaces to establish the framework for the development of a computer system. This framework is established by examining the software requirement document and building a physical model using recognized software engineering methods. The physical model describes a solution in concrete and implementation terms, which is used to produce a structured set of component specifications. That is, each specification defines the functions, inputs and outputs of the component that are consistent, coherent, and complete. An architectural design performs the following functions. It provides a level of abstraction at which the software designers can specify the system behavior such as function and performance. It serves as the conscience for the system as it evolves. By characterizing the crucial system design assumptions, a good architectural design guides the process of system enhancement, indicating what aspects of the system can be easily changed without compromising system integrity. It evaluates all top-level designs. It develops and documents top-level design for the external and internal interfaces. It develops preliminary versions of user documentation. It defines and documents preliminary test requirements and the schedule for software integration. Sources of architectural design. Information regarding the application domain for the software to be developed. Using data flow diagrams. Availability of architectural patterns and architectural styles. Architectural design occupies a pivotal position in software engineering. It is during architectural design that crucial requirements as performance, reliability, costs, etc. are addressed. This task is cumbersome as the software engineering paradigm is shifting from monolithic, standalone, built from scratch systems to componentized, evolvable, standards-based and product-oriented systems. Also, a key challenge for designers is to know precisely how to proceed from requirements to architectural design. To avoid these problems, designers adopt strategies such as reusability, componentization, platform-based, standard-based, and so on. While the architectural design is the responsibility of the developers, participants in the architectural design phase should also include user representatives, system engineers, hardware engineers, and operational personnel. In reviewing the architectural design, the project management should ensure that all panics are consulted in order to minimize the risk of incompleteness and error. Architectural design representation. Architectural design can be represented using various models such as structural model, framework model, dynamic model, protocol model, functions model, structural model, which illustrates architecture as an ordered collection of program components. Framework model, which attempts to identify repeatable architectural design patterns encountered in similar types of application. This leads to an increase in the level of abstraction. Dynamic model, which specifies the behavioral aspects of the software architecture and indicates how the structure or system configuration changes as the function changes due to the change in the external environment. Protocol model, which focuses on the design of the business or technical process which must be implemented in the system. Functions model, which represents the functional hierarchy of a system. Interface design. In this video, we are going to see about interface design. Interface design refers to the design activity that deals with the specification of interfaces between components in the design. Interface design can be focused on specifying the interfaces used internally within software components or externally across software components. In both cases, interfaces provide a standardized way for specifying how services are accessed and provided by software components. Interface design allows subsystems to be designed independently and in parallel, therefore it is typically done first within the detailed design step. External interface design. During the software architecture activity, externally visible interfaces are specified. The realization of these interfaces may involve much detailed design work before they can be used in construction. These may include a customized binary message definition, extensible markup language, that is XML schemas and messages or other interfaces required for specifying how components interact with the other external component. Depending on the interface design effort, a formal interface document can be created and managed independently, similar to the requirement specification or design document. This document, known as the Interface Control Document (ICD), is an important piece of documentation that serves as a written contract between components of the software system to specify how they will communicate. The ICD defines the important data and protocols used for communication between components, therefore providing developers during construction the required information needed to write the software. Internal interface design. The internal interface definition establishes policies for subsequent development in the software design. It provides a way for abstracting common operations so that problems during detailed design can be reasoned in terms of these interfaces, which provides a higher level of abstraction for specifying rules that apply to a larger set of entities that rely on them. In an object-oriented system, Unified Modeling Language, that is UML, can be used to create interface designs using class diagrams that include the interface stereotype in the name section of the class. These help identify the major classes and functions that allow intercomponent communication and provide the rules of communication that must be followed by other classes that implement these interfaces during the detailed design activity. Procedural design. In this video, we are going to see about procedural design. Procedural design begins when data design, system architecture, and interface design is over. This phase is also called component level design or programming phase. In procedural design, we translate the design, that is high level and low level, through a set of programs written in a special language known as coding. The program suite is then executed by a computer system to achieve the specific system objective. A set of such programs, when implemented, is expected to meet the requirements stated in the RDD and SRS. Procedural design achieves the process details to manipulate data structure, affect computations between system components, implement computations based on algorithms. To achieve these results, we have to write programs in a language chosen on some considerations. The program is coded in a language and the process is called coding. Though all stages prior to coding has been done properly, it is observed that in the program coding phase, errors creep in because of bugs in writing the code. Hence, the code should be written such that the program is easy to read, easy to understand, and easy to change through a quick fix so that the debugging time is very short. Procedural design or component level design is a phase in between program structuring and code writing. It provides the means for ascertaining whether the data model, system model, and program structures will work together to produce the intended goal of the software system. Procedural design lays out the details of every processing step of each program by writing a code in a structural form using graphical, tabular, or text-based notation. Once these notations are ready, the code can be written for each one of them in a chosen language. The goal of coding is to translate the procedural design into a source code having key attributes such as simplicity and ease of testing, understanding, and maintenance. The Weinberg and Schumann experiment studied human factors in goals and performance in computer programming and found that programmers have multiple goals and preferences while writing the code. The goals are: minimum effort to complete the program task, minimum number of statements to achieve the task goal, minimum use of resources so that the cost of resources is recovered, maximum clarity, maximum output clarity conforming to the local goal of the task, all these goals are equally important and are not mutually exclusive. They affect cost, resource, effort, quality, and user satisfaction. It is also necessary to note that these goals are language independent but are largely based upon two factors: coding or programming skill and programming practice. One is language skill and the other is methodology of using the language skill to achieve a coding task. Goal achievement is made possible by following good programming practices, which are as follows. Approach to coding, top-down and bottom-up. Structured programming. Use of information hiding principle. Programming style of the program. Internal documentation within the program. Object-oriented design. In this video, we are going to see about object-oriented design. Object-oriented design is a design strategy where system designers think in terms of things instead of operations or functions. Rather than a program being designed as a set of functions that interchange data through their parameters and through a shared memory that is global variables, an object-oriented program is made up of interacting objects. Objects maintain their own local state and define operations on that state information. They hide information about the representation of the state and hence limit access to it. The characteristics of an object-oriented design (OOD) are: in an object-oriented design, a software system is designed as a set of interacting objects that manage their own private state and offer services to other objects. Objects are created by instantiating an object class that defines the attributes and operations associated with the object. The object name precedes the colon in the top part of the rectangle, and the class name follows the colon. Several objects of the same class may coexist in the same program. Object classes are abstractions of real-world and system entities that encapsulate state information and that define a number of operations, alternatively called services or methods, that create, access, or modify the state. Objects are independent entities that may readily be changed because state and representation information is held within the object. Changes to the representation may be made without reference to the other system objects. System functionality is expressed in terms of operations or services associated with each object. Objects interact by calling on the operations defined by other objects. Interaction in arrows linking the objects. There are no shared data areas. Objects communicate by calling on services offered by other objects rather than sharing variables. There is no possibility that a program component can be affected by modifications to shared information. Changes are therefore easier to implement. Objects may be distributed and may execute either sequentially or in parallel. Object-oriented analysis, design, and programming are all part of object-oriented development, where an object-oriented strategy is used throughout the development process. Object-oriented analysis. It is concerned with developing an object-oriented model of the application domain. The identified objects reflect entities and operations that are associated with the problem to be solved. Object-oriented design. It is concerned with developing an object-oriented model of a software system to implement the identified requirements. The objects in an object-oriented design are relate to the solution to the problem that is being solved. There may be close relationships between some problem objects and some solution objects, but the designer inevitably has to add new objects and to transform problem objects to implement the solution. Object and object classes. The terms object and object-oriented are now widely using words. They apply to different types of entity, design methods, systems, and programming languages. However, there is a general acceptance that an object is an encapsulation of information, and this is reflected in my definition of an object and an object class. An object is an entity which has a state and a defined set of operations which operate on that state. The state is represented as a set of object attributes. The operations associated with the object provide services to other objects, that is clients, which request these services when some computation is required. Objects are created according to an object class definition. An object class definition serves as a template for creating objects. It includes declarations of all the attributes and operations which should be associated with an object of that class. An object-oriented design process involves designing object classes and the relationships between these classes. When the design is implemented, the required objects are created dynamically using these class definitions. Modeling using UML. UML offers 5 different groups of diagrams to model a system, much like a set of blueprints used for constructing a house. Different diagrams are used for different types of UML modeling. There are 3 important types of UML modelings: structural modeling, behavior modeling, architectural modeling. Structural modeling. Structural modeling captures the static features of a system. They consist of the following: class diagrams, object diagrams, deployment diagrams, component diagram. Structural model represents the framework for the system, and this framework is the place where all the components exist. So the class diagram, component diagram, and deployment diagrams are the part of structural modeling. They all represent the elements and the mechanism to assemble them, but the structural model never describes the dynamic behavior of the system. Class diagram is the most widely used structural diagram. Behavioral modeling. Behavioral model describes the interaction in the system. It represents the interaction among the structural diagrams. They consist of the following: activity diagrams, interaction diagrams, use case diagrams. Architectural modeling. Architectural model represents the overall framework of the system. It contains both structural and behavioral elements of the system. The various UML diagrams and their purpose are as follows: use case diagram, class diagram, object diagram, sequence diagram, collaboration diagram, state diagram, activity diagram, Object-oriented design process. In this video, we are going to see about object-oriented design process. Abstraction. A model is essentially an abstraction of the real world. It captures only the essential and relevant characteristics of the real world. The abstraction should lead to the development of models. These models should be able to mimic the behavior and form of the physical world when implemented. Just like the real-world understanding of an entity, an abstraction can only maintain a portion of the actual information concerning the entity. For example, if you were to abstract a chair, the common ordinary dining room table type, into a class, you very easily could come up with attributes such as height, weight, color, etc. Design patterns. A design pattern represents a generic and reusable solution to a recurring problem. Design patterns were first published by Gamma in 1995, were able to separate design patterns into three distinct groups. Creational patterns. These design patterns provide a way to create objects while hiding the creation logic rather than instantiating objects directly using new operator. This gives the program more flexibility in deciding which objects need to be created for a given use case. Structural patterns. These design patterns concern class and object composition. The concept of inheritance is used to compose interfaces and define ways to compose objects to obtain new functionalities. Behavioral patterns. These design patterns are all about class-object communication. Uses of design patterns. Design patterns can speed up the development process by providing tested, proven development paradigms. Effective software design requires considering issues that may not become visible until later in the implementation. Reusing design patterns helps to prevent subtle issues that can cause major problems and improves code readability for coders and architects familiar with the patterns. Modularity. Modules or classes are the most important derivation or object-oriented design. This being said, modularity is the use of divide and conquer to create a set of cohesive and loosely coupled modules. This means that each module is an entity on its own connected to the other modules in the system by simple and loose connection. To do this, each module performs a specific function or serves a unique purpose. Any module in this system can be replaced by any other module that maintains interfaces for interconnecting modules.